I think it's because of the sharing with them. You can see this. Maybe I would do this and then restart. Perhaps that would be. Yes.
By turning this off and on again.
Yeah, I'm just restarting and hopefully. Does this work? Well. But the problem is it's not sharing with them. Yeah. Maybe let me give it one more try. That first, let's make sure it's still on the screen. Not this. Sorry. Didn't seem to want to show this. It only want to show the full screen. That works here, but then it's not sharing with them. I actually don't know what to do.
I think you should just continue with the presentation here in the lecture hall, and we will apologize to our Zoom friends.
Nick has seems to, how to do it. Thank you. He's a media musician. I used to consider myself a new generation. So,
where's the? And the problem is that they can't see.
You solved the problem. Thank you.
I think, yeah, hopefully people can see it on Zoom now.
Can you see it? On Zoom?
Yes, we see it now. Thank you so much.
Yeah, thanks to Nick.
Thank you. Thank you.
He does really cool cold molecule stuff and EDM. We'll watch out for him. All right, so we have to keep going. Sorry for wasting some of your time. I think we are here. It's just going through sort of a sidebands and why the red sideband, blue sideband, why with a 50 nanokelvin temperature, we can resolve all these sidebands. Okay, we'll continue. So setup like this finally allow us to do some basic spectroscopy, right? You can see the Doppler effect is gone. It's actually still there. It's that Doppler effect being squeezed and quantized into these sidebands. The carrier is Doppler free, and that you can do spectroscopy with that. The recoil shift is gone because the trap is strong. The trapping force is stronger than recoil force. And you can think of the recoil as being taken up by the photon reservoir. So there's no more photon recoil. The trapping shift, as I explained, was a magical wavelength. The trapping differential AC stock shift is 0. The precision measurement will be improved by square root of how many atoms you can trap there, hundreds of thousands. And that's a significant gain compared to single trap systems. And Jeff actually is known to trap single atoms in cavity QED. And by trapping lots of them, you win by square root of that. And imagine you start to put an entanglement into this. This enhancement is even greater. And that's the excitement that's going to come with the quantum many-body system. So back in 2012, when the precision was continuing to improve, we encountered one problem. The problem is the following. These atoms we actually use as fermions. Some of our condensed matter physicists sitting here will know, well, these in condensed matter physics, the fermions, like electrons, they have pairing, they do Fermi pairing, and the quantum mechanical wave function with regard to a pair of fermions would have to be anti-symmetrized. So suppose I expand one of the pancakes and I got a dozen of the atoms trapped in there. Along the perpendicular direction of the trap, it's so steep, the quantum mechanical motional state is all frozen. But in the transverse direction, the trap is relatively shallow. The trap is, of course, the same depth, but it's the force is much, much gentler. And you have the motional states are not quite in the ground state. And so those have Nj, Ni represents the quantum mechanical motional state in the transverse direction. You got these atoms there, and these are fermions. And when you do clock spectroscopy, you rotate in the so-called pseudo-spin block sphere, spin path, pointing down, pointing up. And you can create a coherent superposition in the equatorial plane. The reason why it looks a little fuzzy is because there's a fundamental quantum noise. When you create coherent superposition and you make a measurement, you do not know whether it's in the ground state. So that's the quantum noise that I'm talking about. If these particles are independent of each other, then each particle has this kind of quantum noise, and it can only average away by square root of the number of particles. And when we were doing experiment like this back in 2012, 2013, what we discovered was, okay, these particles are fermions, and the fermions, as I said, the wave function has to be written up in an anti-symmetrized manner. So if the internal states, ground excited state, is prepared in the symmetrized, or we can call it triplet, kind of a quantum state, then the motional degrees of freedom would have to be anti-symmetrized. So when you exchange the particle position, you will have a negative sign. And so this interaction means the atoms would like to avoid each other, and there's the first partial wave interaction with the so-called P wave, when angular momentum is 1 h-bar. But this interaction turns out to be non-negligible. And in fact, this P wave interaction is not very sensitive to the actual quanta of N. So you can think of this as a collective interaction. And with a collective spin, each one has a spin of 1/2. If you have N particle in there, the total spin is N/2. So now you put this N/2 spins together, they're interacting with each other by this P wave interaction. You actually get them, if you have enough coherence time, you just wait there and they actually become entangled. When I say entangled, it means the quantum noise of each individual particle start to influence each other. And you can see the classical distribution of the sphere, the quantum noise is not being distorted by this Hamiltonian called single axis twisting. This SZ is the Z component of the spin, total spin. And it has a square because it is after this two particle P wave interaction interacting with each other. And this action gives rise to this noise being distorted. At that time, you can actually use this to enhance the clock precision, because as you squeeze this further and further, one of this axis becomes really thin. It's like a squeezed state of light. And so if you turn this into the quadruple measuring the time, measuring the clock, you can actually use this to win. This is exactly towards the end of my talk, will tell you about spin squeezing. But we did not use this at that time because the interaction between these particles turned out to have a P wave loss. The particle will actually be lost during that process, which prevented spin squeezing to reach a very high degree of entanglement. And it's a nuisance in the clock in some sense. These interactions actually provided a so-called clock shift. So if I do not control the quantum system well, this will bring a big problem to the systematic problems of the clock. So we decided to go ahead and avoid this problem by developing a 3-dimensional crystal instead of a 2-dimensional. Why don't I have 3 beams of interfering lasers? And now that by Pauli exclusion principle, if I cool the atoms down to really low temperatures, then each cell, a little cell made by light, will only hold 1 atom. So I can scale up this quantum system if I bring 1 million atoms in there with coherence time of 2 minutes. Well, it turns out you can achieve remarkable precision with clock, 4 × 10⁻20 at 1 second. This was at the time when we were thinking about building a system like this, but the clock was sitting at 10⁻16 level. So this is a several orders of magnitude beyond what we could do, but it was also very exciting because when you reach the number of 10 to minus 20 and so on, you start to look at LIGO's number, LIGO's 10 to minus 21, 10 to minus 22 sensitivities. You start to think, well, maybe one day, quantum sensor like this can actually be used to detect gravitational waves if we could actually integrate all these atomic physics package into a satellite and flying. And I have to say, really happy to tell you, over the last 7 years, we actually did push the clock stability by 2 orders of magnitude, now sitting at a 3 times 10 minus 18 at 1 second. It will take 10 to the 4 seconds to average it down to 10 minus 20. But this is exactly what we are going to do to actually use this to measure gravitational redshift. But I'm also very, very pleased to say, that our field is very innovative, very creative. People love each other, and this young people, and I call him Manuel here as young, and Adam Kaufman. There's no way this was not showing respect. The youngest being like physically, he is younger, but his sophistication maybe is older than me. These people have created this new clock called optical tweezer clock in just a number of 2 years or something. I believe that I was actually sitting in Michel Lukin's office talking about this, and Michel was saying like, "Oh, I have a young postdoc who's about to go to Caltech," and I say, "Congratulations, Manuel and Adam Kaufman. They won the 2023 New Horizon Physics Breakthrough Prize." I was actually serving on the committee, and they actually wrote a citation for these 6 people. They were among 4 others who just done amazing physics with tweezers and being recognized. So it just shows how vibrant the field is that's moving forward. So coming back to the lattice, now that I have a 3-dimensional optical lattice, I showed you that you can quantize Doppler motion. Now I'm going to show you can quantize interactions as well. Remember the interaction was kind of giving me some trouble in the clock's accuracy. Well, now again, I'm showing you the picture of the motional degrees of freedom. That is no longer news. This is something you saw in the 1D, except you see three sets of sidebands because there's 3-dimensional tracking. In all 3 directions, you are in the ground state. If, however, the strontium-87 fermion has like 10 different nuclear spin states, and these nuclear spin states do not interact with electronic degrees of freedom because electronic angular momentum J equal to 0. So that means you can put a different colored, if I use color to represent different nuclear spin states, different colored nuclear spin atoms can sit on top of each other, right? There's no cost because they are not identical fermions. There's no Pauli exclusion principle. But there is energy cost because the 2 atoms sitting in the same lattice will interact. And so when we do spectroscopy, you can actually see the interaction is now quantized. You can see there's a 1 sideband here, the other sideband here. This is because there are 2 atoms sitting in this well, and one is anti-symmetrized in the nuclear degrees of freedom. The other one is symmetrized in the nuclear degrees of freedom. Remember, the overall wave function has to be anti-symmetrized, but anti-symmetrization can come from either electronic side or the nuclear side. And that's why you see 2 sidebands. And what's remarkable already telling you that you have 10 different colors, and because this SCON symmetry, this is the term that we learned from high energy physics. It doesn't matter which 2 colors you've used to make a pair. The interaction is always on the same side. It's the symmetry. And in fact, we can push this all the way out to 3 atoms sitting on the same side, 4 atoms sitting on the same side, 5 atoms sitting on the same side, and it only sees 2 peaks. One's anti-symmetrized, one's symmetrized. In fact, there are those very entangled states you have, and you can see those spectroscopy can resolve them. Not only you can resolve them, once you can resolve them, you can actually pick those atoms and say blow away every other atoms. You can have 4 atoms, 5 atoms left in your lattice, which is strongly entangled in their nuclear. That's just an interesting quantum physics phenomenon. And we also learned this turned out to be a really important tool, which is take a lot of good images. And we have this incredible spectroscopy resolution. We also build a very high spatial resolution. So really kind of looking into the guts of these atom many-body systems. And here shows a picture of so-called band insulator, 3-dimensional band insulator, meaning these are fermions. If you can only have 1 atom per side, nuclear spin is polarized. Then as you put more and more atoms in there, you can see the central part, 1 atom per site is filled up to 1. And if you want to put more atoms in there, it becomes like a wedding cake. It expands out, and the top is flat. And this is telling you this is sort of the band insulator is forming in the 3-dimensional space. You can apply a little field gradient, like magnetic field. And when you have a magnetic field gradient, the Zeeman energy is shifting, and you can actually freeze by using lasers to coherently excited atoms. You can see the blue, red stripes indicating some atoms here is excited, these atoms are in ground state, these atoms are excited. And by measuring this, just counting the grids, you can actually measure the field gradient. Later on, I'm going to use this trick to measure gravitational field gradient. This is the magnetic field gradient, but gravitational effect is much more interesting. Another aspect is, these atoms have very, very small dipole moment, because those are so-called forbidden transitions. So that dipole moment is 1 microdivide. The interaction energy is very small, but turns out when you have the laser light coming in to prepare these atoms in coherence proposition, there's a dipole interaction mediated by this retarded potential of e to the ikr over kr. K is a wave vector, I is the distance between the particles. And so probably some of you have heard of so-called Dickey model, where the atoms, individual quantum particles are spaced apart, and they are all interacting with each other with dipole interaction that would lead to so-called superradiance. And in this case, superradiance is just dissipative aspect of dipole coupling. The reactive part of the real part of it is actually frequency shift in the clock. Remember, these are microdivide interactions. Square of dipole moment squared is 10 to minus 12 compared to 1 divide dipole moment. And if you talk to Manuel Angeles, he will say, why are you dealing with these small dipoles? I will have a Rydberg atom that would have dipole moment of a kilodivide. And so we are talking about energy scale that's 16 orders magnitude or something like that, smaller than Manuel Angeles. Yet, if you had a patience, this small dipole moment gives rise to actually very strongly dipolar shifts. When I say strongly dipolar shifts, these are 10 to minus 19, 10 to minus 20 kind of clock shifts that we can measure. But the point I'm belaboring this a little bit is, this is really interesting to me. You're building clock, you're trying to tease out all the noise. And in the end, as long as I'm not building quantum computer, as long as I don't care about the gate speed, well, this coherence time is really what matters in terms of how you are going to see the emerging phenomena in mathematical probability, many-body physics. And this is what we are showing, sort of a collective dipoles. We can flip a dipole to the North Pole or the South Pole, and you can see the pattern just taking the image from upstairs. You can actually see the atoms on the right-hand side gets excited, or the left-hand side gets excited, depending on the dipole, how you're flipping it. So these are actually quite exciting results we're just starting to prepare to write up. And I just want to make a quick connection. It's like, large array of radio telescopes, you have phase coherently connecting them. And this is exactly what this is, except that these are individual quantum particles. You can, in principle, go in and address individual one of those. And if you flip one, you actually will have some quantum phenomena emerging. So with that, I want to tell you a little bit about clock comparison as we move towards how entanglement can help with clock comparison. There are 2 ways to do clock comparisons. One is so-called common local oscillator, which means if I have the same laser driving 2 atomic systems, well, the laser brings some noise into the system, but because it's a common drive, it's a common noise. So I can remove it. I can make a direct comparison between the atomic systems. On the other hand, not all clock comparisons done by this using atom against atom. In fact, the real atomic clock people compare where you do not share the local oscillators together. They have separate local oscillators, and in that case, we often compare is a frequency ratio. And I'll give you a couple examples of this technique 2 first, and then tell you about technique 1. In technique 2, back in 2008, Victor Flambaum from Australia came to visit our lab, and he said, Jun, why don't you think about doing an experiment called the local Lauritsen invariance, which is when Earth is rotating around the sun and the gravitational potential changes by 5%. He said, if you compare clocks, maybe you can measure whether the fundamental constant is not a constant as you get from gravitational potential. This will be checking against each so-called fall universality of fall or local Lauritsen invariance. So we can indeed do a clock comparison between Boulder, Paris, and Tokyo. We are trying to compare strontium clocks. Those 3 labs have strontium clocks, but there is no infrastructure allowing you to compare optical clocks directly. So what do? We measure frequency ratio against cesium. So when we say clock comparison, really this is a strontium against cesium frequency ratio being compared between 3 labs. And the cesium clock, on the other hand, is connected by GPS between different continents. That's how we can make a clock comparison. In the future, I'm going to tell you something else, but this was what we could do in 2008. And you can see the ratio of the 2 or 3 years allow you to place a bound of whether the fundamental constants really is oscillating as the Earth is rotating around the sun. Of course, we didn't see that. It's just a place upper bound. And at the time, this was the best upper bound of so-called linear drift or sinusoidal oscillations of the fundamental constants depending on the gravitational potential. These days, people have pushed this down now to 10⁻17, 10⁻18 level. But the clock comparison we have over the last few years really advanced to the point where now we can compare some of the best clocks in Jella and NIST, which are about 1 mile apart. We can connect them by a piece of fiber where the laser can go back and forth. We can also actually directly shoot lasers. Our lab is down in the basement. We can connect up to the 10th floor and use a telescope to shoot laser beams to another building in NIST. Of course, the first thing you have to do is talk to the city of Boulder to make sure it's a bird's eye safe. The bird will be flying through this. But you have to stabilize. Boulder is famous for very gutsy wing. So you have to make sure that the wing does not cause frequency perturbation. Of course, it will, but we can compensate for it at the level of 10⁻18. So we cannot compare those clocks. Why this technology is important is imagine if finally I want to compare clock in the US against clocks in Europe, Asia. Are we going to build through the fiber, or is it better to just shoot a laser beam 10 kilometers, it will clear the space, and finally satellite to satellite thing will allow it to function. So this is really the technology of the future. This is a 1 kilometer long. If you extend this by factor of 10, you are clear of the atmosphere, you are in the space. So the people are working now, multiple teams on 3 continents are working on this kind of technology to connect to the final to the satellite. JPL can play a big role here. So when you do clock, you can see here's a free space comparison between ytterbium, strontium, you can average it down to 10⁻18 level. Not only this kind of a clock comparison is important because SI unit depends on second. There will be a redefinition of second coming soon with optical clock instead of the cesium clock. And in order to do that, we must have the network of clocks that we can compare reliably. But of course, there's other whether it's industrial process, advanced navigations, communication networks, or fundamental science that's all require this clock network. And that's without saying this is an important piece of technology that we need to develop. But on the fundamental science side, maybe just a quick slide on if you can compare different atomic species of the clock frequency, you can actually place a bound on ultralight scalar dark matter because, say, a kiloton as a candidate for dark matter, this is a scalar field that can modify fundamental constants like fine structure constant alpha. By comparing different atomic species, they're comparing different atomic orbitals, for example, and they have a different sensitivities to the fine structure constant if that's changing because of dark matter field happens to be penetrating through the Earth. You can just look at the fractional frequency change between different clocks, and that will tell you whether delta alpha is changing. And this will allow you to use the ratios to place the bound on the possible coupling strength of dark matter to ordinary matter and ordinary field. And indeed, this is true. Now, some of the best limit of the dark matter in this energy scale of 10⁻20 to 10⁻16 is not indeed set by this 3 clock comparison or our strontium clock against silicon cavity. These are now placed as the best bound on the possible dark matter coupling strength. Coming back to the clock comparison where I was telling you, I do not have to use separate lasers. I can use one common laser and allow me to compare 2 different atomic species directly. In that case, I'm going to show you a final example of the experiment with which we actually have lowered the trapping depth significantly to a regime where we are now creating a so-called Varnier-Stock lattice. And I will explain that a little bit to you, what I mean by Varnier-Stock lattice. So we typically use lattice trapping depths significantly deep, something like 30 microkelvin or so, 50 microkelvin. And these atoms individually trapped, they cannot tunnel, because the trapping depth is sufficiently deep. Now, what if I start to lower the trapping depth? The reason why we were lowering the trapping depth is when you have such a strong trap depth, there is actually a little bit of photon scattering going on the excited clock state can do Raman scattering to other atomic clock state, limit my coherence time instead of 2 minutes. It actually is significantly shorter to like 10 seconds. So I was very motivated to try to lower this trapping potential. And as we lower the trapping potential to lower and lower, and nowadays we actually now lower the trapping potential from 100 recoil energy. This is excuse me for using this unit. The photon recoil as energy for strontium is like a few kilohertz. We typically use 100 photon recoil kind of energy scale to describe our trapping depth. And now we lowered it by more than factor of 10. The trap is so shallow, and we actually had to use cavity to suspend it to make sure the waveform is really flat and everything. When it's so shallow, the wave function actually now spreads out. It's no longer just you can think of as an atom. It's actually a wave function that's occupying several different neighboring sites. And remember, we said there is the magical wavelength. So the ground state is here, but there's excited state which experiences the exactly same trapping potential. Now you can imagine as you drive the transition, the atom could be in the same site, but it can also drive the quantum mechanical wave function superposition from one side to the other, because you have an appreciable wave function that's spread out there. So you can create this weird coherent superposition where one half, when the created superposition, the atom is sitting, the ground state sits here, excited state sits 10 micron away, somewhere else. And they can being suspended there with coherence time of nearly a minute. You can immediately think of this can be a clock, or this could be an atom interferometer. They experience the phase shift of the gravity. When you look at the spectroscopy, this is not a theory curve. This is actually experimental data. It looks like a noise-free. That's because the lines are exceedingly narrow. This is the so-called on-side transition. And then you see sidebands. This sidebands is now nothing but what we learned in high school. When you lift a particle against the gravity, there's a gravitational potential energy. So this energy, this difference is nothing but a mass times g times the height difference, lambda/2. Okay, so this is a very classical energy difference. It's not a gravitational redshift or anything. This is just telling you a different pancake that's sitting at a different gravitational potential energy. And we can resolve them. The key question is how good a coherence this is. And it turns out we can do this imaging spectroscopy I described earlier. This atomic cloud is about millimeter long. And you can divide yourself into two halves of this, the top half and the bottom half, one the two different regions. We put about 100,000 atoms in there, and you just take an image of those when the atoms are being excited by the common laser field. You can think of this as nothing but looking at two sets of quantum pendulum that's oscillating back and forth in the top half and the bottom half, and to see whether they are keeping in coherent superposition. So, for example, if you waited for 30 seconds, you put these atoms in coherent superposition and just watch them oscillating. 30 seconds later, you can see if you plot the bottom axis of the excitation fraction versus the top axis of versus the top half of the atomic cloud, and look at their coherence superposition, you can still see very clear phase coherence, right? This ellipse is telling you, they're basically the both pendulum are still doing this, but they start to develop a little bit of phase shift between them. That's why you start opening up a little bit of the area under this ellipse. If you wait 50 seconds, you can still see the coherence synthesis. It's really telling you these quantum pendulums, if you have no laser noise, these systems are really in coherence superposition for that long. And with such a long coherence time, you can start to really tune the atomic interactions. And in this case, remember in the earlier slide, when I had a single pancake slide, there was P-wave interactions I described very quickly. It was a fermionic interactions. But now with the lattice side being so shallow, these atomic wave functions spread out, and you can, because of the clock wavelength and the spacing between the lattice sides is not commensurate. So atoms between different layers actually have a different clock laser phase shift. These are no longer so-called identical fermions. And that means neighboring pancakes can interact with so-called S wave, right? You do not have to anti-symmetrize the wave function when those particles are distinguishable. So by tuning the depth of the trap, you can tune the relative contributions of S wave versus P wave. And if S wave and P wave have opposite sign, the consequence is as you tune the axis of the lattice intensity or the depth of the lattice, the interaction energy can be tuned from negative to positive, going through zero. And going through zero means you can make a clock frequency shift be free of atomic interaction. These atoms are still interacting. It's just that your S wave and P wave are balanced to such a degree that you can no longer see it. And this is, in some sense, it's a really nice quantum state engineering that these interactions can be tuned by one of the knobs in our lab. And so with this, we can actually finally start to measure the actual relativity effect, general relativity effect, by again comparing the top half versus the bottom half of the two clocks. So we can just divide the 1 millimeter atomic clock into two different sets of the clocks and compare them. And you can see that this is averaging down to something like 6 times 10 to the minus 21 per clock. And the gravitational redshift is 100 at a 10 to the minus 20 for 100 micron distance difference. And so you are really starting to measure these time is being different of the time dilation effect at this very small scale. And so this is the measurement of actual gravitational redshift. Shimon Kokowitz's group at the time did not measure the gravitational redshift at that time when they published the paper with us, but now they have since also measured the gravitational redshift by moving the clock by a centimeter also. So the reason why this, to me, this is very exciting is the following. This artist showed the time is very soft. This is not true. Time has always been soft. It's not we just become more perceptive to it. What if I can start to measure time difference redshift on the length scale of a single quantum mechanical waveform? And would that be able to see something really interesting? I think, if you look back when Einstein wrote down e to the mc squared, now, of course, this has a real impact in our current precision of the clocks when the atom absorbs a photon going from the ground state to the excited state. The mass of the atom changes. The ground state is m strontium. The excited state has now the rest mass plus h nu of a c squared. And this difference, if you write down the single particle Hamiltonian with the gravitational field of the Earth, what actually tells you is directly allow you to derive the motional time dilation as well as gravitational time dilation. That perhaps is not so interesting. And this, by the way, this mass scale change is 10 to the minus 22. If you absorb the photon, and the change is 10 to the minus 22. But what if now we start to think about the spin model I've been telling you? I didn't mean to, explain this math, but I just want to show you. If you have atoms in a single pancake, they are all interacting similarly. They're the same fermion because they have a common gravitational potential. Because now we have, in the Hamiltonian, we have to add this GR term, general relativity term, which depends on each pancake. You have a different redshift. But the interaction between these sites, the called S wave interactions, these interactions now have additional phase shift due to the gravitational potential. So you can see that with the gravitational potential, you can have terms which is commuting with the GR term in the bottom, the red, or you have terms of the Hamiltonian, many-body Hamiltonian that's not commuting with the GR term. And these can be measurable at the 10 to the minus 20. We actually calculated the magnitude at the 10 to the minus 23, 10 to the minus 24. Not quite at today's precision, but you can see those are linearized gravity, will have impact on many-body quantum physics. It's not quantum gravity whatsoever. There's no quantum noise But nevertheless, it's if you had an entanglement which on a single pancake, that's horizontal pancake versus a pancake which is the vertical, they will have a different dynamics by gravity. And to me, that's starting to make a connection between quantum physics and gravitational physics. So in order to do this, now we have a final trick. We have to improve our clock further. And this comes back to this quantum noise that I showed you earlier, where you put yourself in coherent superposition between grounds and excited state. You're measuring that little phase, e to the minus e to the I t, et. E is the energy difference between the two clock states. In order to make that measurement, you're rotating this along the equatorial plane, this coherent superposition, and then read out by a phase coherent laser. But there's this fundamental noise. So this is what I mentioned earlier. There's a standard quantum limit scales 1 over root of particle numbers you have when they're incoherent. But what if you can start creating entanglement? And one of the key benefit of entanglement is actually these atoms sort of conceal each other's noise, such that instead of n copies of a quantum noise, you have only 1 copy of a quantum noise if the entanglement is perfect. And that will allow you to reach the so-called standard quantum limit in scales as a 1 over n instead of 1 over square root of n. And that would be a big gain if especially n is a big number. And we have learned from some pioneers like Eugene Posick, which was shown in the picture with John Preskill earlier, Vladan Vulitic, Mark Kasevich, and James Thompson, and so on, about spin entanglement, right? The spin squeezing. But those have been only done in sort of a proof of principle or demonstration experiments. Is it possible we can actually do this experiment in the state-of-the-art clock experiment? No, so meaning spin squeezing actually demonstrating its advantage at 10 to the minus 17 level. And you can do direct clock comparison. You do not have to subtract noise. You do not have to make a claim after you say, well, some of my technical noise is masking it. If I remove that noise, the quantum gain is there. We want to show directly metrological gain. And so we came up with a scheme shown in the middle, where this vertical lattice is now made to be able to move up and down like an elevator. And we can load atoms A and move them up into the cavity. This is the high finesse cavity, which allows you to do cavity QED. And all of that used to be downstairs here, the optical cavity QED. And we can then move the sample A once it's entangled, move it out, and put a sample B inside. The reason why, if you want to know the more details about experimental details about entanglement generation, I can tell you. But essentially, in one sentence, it's using the collectiveness of the many, many atoms inside of this high finesse cavity that gives rise to quantum non-demolition measurement. You can actually see the presence of atoms in there without destroying the quantum superposition. So if you do that, then you have 2 entangled ensembles. You can make a direct comparison of the clock, because this actually is as you can see, a one-dimensional optical lattice clock. And so I want to give a shout out to Caltech, because I learned all these tricks here with Jeff Kimball. And this was the picture Professor Preskill helped to organize. And this is the photo that he's standing right there to the left in the front row. And Jeff Kimball sitting in the white shirt guy in the middle. And it was his work of 20 years at Caltech, established optical cavity QED as a real strong coupling quantum physics that now allow us to take advantage of it. I think many people came, John, that we can be very proud of that particular location. At that time, there was before Kip discovered gravitational wave. And he gave a talk, I remember, a really interesting talk about the anticipation that things is going to happen soon. And 2 years later, of course, happened. So just want to thank Jeff and Caltech for the education here. And this is what I mentioned earlier. We can now have 2 different samples. We can entangle one sample, move it out, entangle the next sample, and the data shows a direct clock comparison. The top green square is the classical computer, classical quantum system. Classical systems, we do not do quantum entanglement. The black dots are actually entangled spin squeeze, the clock comparison. It's a feeble, only 2-3 dB of gain, but it is averaging down no longer at 10 to the minus 12 level, but approaching 10 to the minus 17 scale. And I think that this is the very beginning. We only put the 1,000 atoms in there. We know exactly how to scale the system up to gain further by quantum efficiency and so on. So to me, this is actually very exciting. Entanglement can really start to play a role in state-of-art quantum sensors. So with that, I think I'm at the end of my talk. I know if anything, the Caltech spirit has always been go big, dream big. And I think we all share that. The clock when we make more than just a timepiece to keep time, but it actually becomes a telescope looking into the fundamental physics, dark matters. Certainly we can learn from LIGO as our inspiration for gravitational wave detections. We can build a clock network if one day this link works and the clocks can sitting in the sky and beam down the time to us. And you can turn this into a network to help monitor the Mother Earth, the environmental changes, because as we described, time and gravity is interconnected. So you can use this to Earth's geodesy as a microscope. So thank you for your attention. I want to thank many colleagues in the lab, students and postdocs, and as well as collaborating long-term collaborators. Anna Maria Ray has been a strong theory collaborator, as well as some of the colleagues in Java, Adam Kaufman, James Thompson, and then yes, PTV is actually German standards lab with whom I have had a long-term collaboration on strong silicon capital. So thank you very much for your attention.
Thank you, Jim. We have a reception set up to celebrate the Lauritsen Lecture right at North Bridge, which we'll all want to join in a minute, but the duration of Jun's talk got squeezed by our technical difficulties. So maybe we can take a couple of questions before we go on to the reception.
Managed to anti-squeeze it by extending the time a little bit. Sorry for that. Oh yeah, hi.
Does it show exactly I understand that synchronize the rate of patterns expression does it show
Does not include accuracy of the clock. It includes the precision of the clock. That allows you to average the noise away faster. But the actual accuracy is limited by systematics. In fact, these are the things we always do. But the clock, in fact, as a quantum sensor, not just accurate is important. It's actually precision. Actually, in some ways, it's almost as more important for fundamental physics. Like if I want to turn this into say gravitational wave detection, I don't really care if this actually is accurate. I just want to make sure I have two clocks agree with each other. And then as I'm averaging noise away, I can see when the gravitational wave comes, there's a clock difference. So yeah. That's correct. Yeah, your averaging time. So this is the quantum game. Is like you can turn with a finite particle numbers working for you. The averaging time in principle is square root of tau. And the n is not 1 over square root of n times tau. Will be 1 over n times tau. So it will be much shorter.
One up here, Manuel.
Oh, here's the young man. Yes. Yes.
because of this?
That's exactly right. Exactly. If you had a laser in there, the laser noise was totally swamping. Then, in fact, if you look at the Lauritsen result, his clock comparison is at 10 minus 12, and in many ways was because of laser. So even our laser is much better than Lauritsen. Still, that was going to limit us at 10 minus 16 and so on. So we removed the common laser noise out by directly comparing two atomic ensembles directly. In another way, you can think of like a laser created coherent superposition, And the laser noise is essentially saying when you make a measurement, the two ensembles are moving like this, but they are moving. Yeah, so what you're referring to when you say stand-alone clock, meaning in that case, the laser has to be slave. So we will have to like build yet another system, which the only goal is to making sure the laser is always keeping track with the quantum coherence. And so that's actually part of the strong motivation why we want to keep pushing the limit, state of the art of the laser. Now, why it was emphasized so much, I want to have a laser with coherence time of 8 minutes. And it's really for experiments like this. And the other thing is, in principle, you want to build a quantum system where you can run continuous. Every time you stop for a second, there's a little phase jump, and then there's tick noise, because our famous colleague from JPL. And so that's something, another thing that you want to talk about, some sort of quantum resource where these atoms can, in principle, always be available to you.
Jun, how far can we go? 10 to the minus 20 now, 10 to the minus 21 tomorrow, but that's not the end of the story.
That's not the end of the story.
We look out 10, 20 years, what can you envision?
I would love to get to the point where the clock is getting to the stochastic noise of gravitational wave. That's 10 to minus 27 to minus 28.
That's as far as you can go.
That's well, I think we won't be able to get to the Planck fluctuation all the time, but it probably will be stopped by gravitational wave.
This time is too bumpy.
Too bumpy. Yeah, it's actually now you said this, it's kind of really interesting. You know, imagine when the British Royal Navy, when they want to kind of go out in the ocean, the pendulum clock no longer works because the ocean is too rough, and they had to invent this chronometer. And finally, they were, this was actually part of Industrial Revolution, right? And I think it's kind of ironic that in the end, the quantum physics, no matter how much you do, in the end, it's going to be limited by the roughness of the universe, of the, gravitational.
Oh,
That's many years down the road. Yes, maybe
We'll get there.
Here, what is that?
Look, for those of us who care about the accuracy as well as the precision of clocks, I guess it's time to wind this up. But please join the reception.
Thank you.
Great talk. Thank you so much for
Thank you.
coming back.
You have some good graphics.
Yeah, some of them I made myself. Yeah.
Impressive.
Beautiful talk,
Oh,
so
thank you.
nicely
Thank you.
delivered.
Good to see you.
I was going to ask you, so this idea of you start with these deep trapped atoms, and then you figure out to make the trapping shallow, and then you make them one. I mean, okay, great. I mean, that's where the breakthrough is.
Yes,
right?
exactly.
Yeah, you came up with that idea?
We didn't come up with this. This was the idea that
I just thought it was so clever.
people came up in 2005, but nobody touched it. And that's because everybody felt like when the trapping potential is so shallow,
Yeah, you were worried.
it won't work. Yeah, exactly.
Usually it's just counterintuitive.
Yeah.
But turns out you take advantage of that.
Yeah. And what's
Theory.
beautiful is, of course, it's retrospectively thinking back, it works beautifully because it's a coherence position of a Wannier orbital,
Right.
and it has to be coherent. So
Yeah.
I think we were the group who's decided